This is Xiang from NVIDIA. I'm going to present our work, Learning RGB-D feature embeddings for unseen object instance segmentation. For a robot to work in unstructured environments, it will encounter objects it has never seen before. The question we're interested in here is, how can we train a model to segment unseen objects in images? In order to segment arbitrary objects, a robot needs to learn the concept of objects. This is usually achieved by learning from data with many objects. However, the large-scale dataset in the literature, such as ImageNet and CoRL, consist of internet images. They are not suitable for indoor robotic settings. Therefore, we resort to using synthetic data for learning the concept of objects. For example, we can generate a large number of images using ShiftNet models in a physics simulator, but in this case, we need to deal with the sim-to-real gap. Previous works on learning from synthetic data show that learning from synthetic depths is easier to transfer to the real world. The key question we're addressing here is, can we utilize non-photorealistic synthetic RGB images to learn a useful model that can transfer to the real world for unseen object instance segmentation? Because for certain objects, we cannot obtain good depths for them, such as transparent objects and seen objects on a table. We introduce a novel method to learn RGB-D feature embeddings for unseen object instance segmentation. In our method, a fully convolutional network is applied to extract a dense feature map from RGB-D image, one feature embedding for each pixel. In training, our goal is to learn feature embeddings such that pixels of the same objects are close to each other and pixels of different objects are separated in the embedding space. We apply metric learning loss to learn the embeddings. Our metric learning loss function consists of an intra-cluster loss and an inter-cluster loss. First, we compute the spherical mean of the case objects. We use cosine distance in the loss function since all the feature embeddings are normalized to have a unit length. The intra-cluster loss minimizes the distance of each pixel to the clustered mean with the margin alpha, while the inter-cluster loss maximizes the distance between the clustered means with the margin delta. We investigated 3 ways to fuse RGB and the depth image. In early fusion, the RGB and the depth images are concatenated before feeding to the network. In late fusion addition, 2 networks are separately applied to the RGB image and the depth image. Then the 2 feature maps are summed together. In late fusion concatenation, the 2 feature maps are concatenated to obtain the final feature map. We propose a new 2-stage clustering algorithm to segment objects. In the first stage, mean shift is applied to all the pixels. In the second stage, mean shift is applied to a region of interest for each segment from the first stage. The second stage clustering is able to separate objects close to each other or on top of each other. It can also sharpen the segmentation boundaries of the objects. For experiments, we tested our method on 2 datasets for unseen object instance segmentation, the OCLD dataset and the OSD dataset. We first investigate the effect of the input mode on the 2 datasets and compare with mask RCN. 2 metrics are used here, F-score for region overlap and F-score for boundary overlap. Our method achieves the best performance using RGB-D late fusion addition. This experiment shows that our method is able to utilize the non-photorealistic RGB images to improve the segmentation accuracy. We investigate the effects of our 2-stage clustering algorithm. We can see that the second stage clustering is able to significantly improve the F-score boundary for all the 5 input modes. Finally, we compare our method against the state-of-the-art method for unseen object instance segmentation. Our method achieves the best performance on these 2 datasets. We show some qualitative results from our method. Comparing the initial labels from the first stage clustering and the refined labels from the second stage clustering, we can see more objects are separated correctly in the refined labels. Here are some failure cases from our method. It oversegments a keyboard and a power drill in the dataset, and even with the second stage clustering, it cannot separate objects close to each other in some challenging cases. Here is an anecdotal example showing that our method can also segment transparent objects using RGB images. In conclusion, we introduced a novel method for learning RGB-D feature embeddings from synthetic data with a metric learning loss that transfers well to the real world. Adding non-photorealistic RGB images to depths can improve our method. Using RGB images can handle objects with bad or missing depth information, such as transparent, flat, or thin objects. Thank you for watching.